Hey, good morning, everybody. Thank you, Jason, Corey, Matthew, Brandon, Angela. Thank you. Thank you, Fox. Okay, Ronald. Thank you, Ernesto. Well, today I want to talk about complex functions, right? Now, here is uh, what do I mean by a complex function or a function of complex variables, if I want to be more accurate. Okay, so as the name indicates, um, you have a function. Let me give you an example. So functions of complex variable. So here's one, f of z. Now, in calculus, you had f of x. X was a real uh, number. But here, we are going to have an expression in z, and z is a complex number. Make it very simple. Here is a very simple one, z squared. Okay? So remember, this z is a complex number, and z itself looks like this. It has a real part plus I imaginary part, okay? If we replace z in here and do the multiplication, this is what we will get. So f of z is going to be x plus iy squared. Now let's multiply out. You will have x squared. This is squared, but I squared is -1, right? So negative y squared. Then twice this times that, so 2i xy. Now let's see what happened. Of course, the result here is a complex number, the output, okay? This is called the input, and this is called the output, the value of the function. This complex number has a real part, which is this one, an imaginary part, right, which is 2xy. Well, in general, a function of complex number or complex variable can be written as its real part in terms of x and y plus I, the imaginary part, let's call it v xy. So what are u and v? U and v are functions of two variables, but the variables are real. Now, we go back to calculus 3. In calculus 3, you saw these type of functions, right? The domain of these functions are part of the plane, and we expected that. Well, so in summarizing this, I will call this one u plus iv, okay? When I write this function in this fashion, a lot of good things will happen. One of the good things is about taking limit of this function. The other one is talking about the continuity of the function. All right, these terms are coming from calculus. You have seen these terms anytime. Okay, let me make sure that we understand what's going on. Anytime you have a function, either real valued or complex valued, there are some concepts involved. The first one, remember, is finding domain of that function. What is domain of that function? Then, of course, we want to find, if we can, we want to graph that function, find a picture for it, a geometric picture for it. And then the question is, what is its limit? Okay, the concept of limit applies to it. And then, of course, after the limit is continuity, whether this function is continuous or not at certain point. Then, of course, when you just go through the concepts that were introduced in calculus, the next one is, oh, can we have derivative? Right? The next one, of course, integration, right? Antiderivative, integration. So, antiderivative. And integration. So all these will apply to a function. You got to have a function to talk about those concepts. So the function is the major point, the major ingredient in calculus and complex analysis. All right. Okay. So I want to talk, for example, about graph, or well, we will talk about graph later on, but limit continuity at the moment. But in order to talk about limit continuity, I want to emphasize about one very interesting inequality. Okay, one interesting inequality. So if you have a complex number u plus iv, its modulus, if you remember, the modulus of this w is the square root of this square plus this square. Okay? So under this radical, we have u squared plus v squared, which are two non-negative quantities. So definitely this will be bigger than or equal to each one of these, right? So the first part of inequality that I like is this, that modulus of w, which is this one, is bigger than or equal to either u, the real part, or w. Did I say w? I thought, yeah, I had v. Okay. All right, better. On the other hand, the other side of inequality, See, here I can add certain things in the under this radical. For example, I can say, look, this is less than or equal to, add something right here, which is u squared plus v squared, right? I am adding now twice u times absolute value of v. If I do such a thing, right here, under this radical, this is a perfect square. And this is actually u plus v square. And then you take a square root. So you will get u plus, right? This is the inequality that I'm going to use to talk about the concept of limit and continuity of a complex variable function. Okay, how? Here is how. We have this inequality is going to behave like a miracle for us, as you will see momentarily. Okay. So here is what I had, all right? Here's a justification. Now, going back to the limit. When we say limit of this function, as z approaches z naught, it's a complex number, is L. This is equivalent to saying that limit of the difference between these two is 0, right? This is very crucial to know. So when we say limit is L, it's the same as saying limit of modulus of f of z minus L is 0. All right. Now I am going to expand this. Let's say the function is right here, u plus iv, and L is a complex number. So the limit is L. So put it in here, in this modulus of f of z minus L. If I do that, this is what I get. This is f of z minus L. So u plus iv minus L. Putting reals together and imaginary parts together, this is what we get. Now, I'm going to use this inequality that I talked about, right? This inequality right here. So here you have a complex number, this, minus I this. So it is less than or equal to the real part plus the imaginary part, absolute value, of course, and bigger than or equal to either one of them, all right? Either one of them. So far, so good. Now, what happens if the limit here be L? The limit is L. That means when you take limit of this one, you get 0 here. As a result, limit of this guy and limit of this guy will be 0. Okay? Now, limit of this guy being 0 means limit of u is A, and here limit of v is b. Okay, so if the limit exists, the limit of real part and imaginary part also will exist and is A and B. Now, vice versa. Suppose we already know that limit of u is A, limit of v is B. Then when you take limit, here you get 0. And here, of course, it's bigger than or equal to 0. By squeezing theorem, limit of this guy will be 0, which means limit of f of z is L. Okay, putting all this together, we have this beautiful fact that limit of a complex function is a plus bi if and only if limit of its real part be a, limit of its imaginary part be b. And this one will take us to calculus now. All right? So in order to take limit of a complex function, like a function of complex variable, you only need to concentrate on its real part and imaginary part. And that is when you go to calculus 3. Okay. Any questions so far? All right. Thank you, Jason. I don't see any question. So I will continue with after this conclusion. So now taking you to calculus 3. Okay. In calculus 3, you have a function of two variables. You take limit. And of course, the limit of this is L, means limit of this one is 0, no doubt, okay? I'm talking about x, y approaching to x0, y0. Now, there was a very interesting theorem and very interesting fact in calculus 3 that I would like to remind you. It's just a little review. And those of you that have time and would like to review more, please go ahead and review the facts that you learned in calculus 3 concerning functions of two variables. So, to show that this limit exists, we will form this one, and we prove by going through some logical steps that the limit is 0. But you try to do this, you try to show that this limit is 0, but somehow you cannot. Then you suspect that maybe the limit does not exist. All right, then you want to prove that this limit does not exist. So how do we prove that the limit does not exist? We choose two curves that are going through this point, and we will stay on those two curves, and we will take limit. And we will produce two different results, okay? Two different results. Here's an example of what I said. So we want to show that this limit does not exist. Well, first, I will stay on x-axis. When I stay on x-axis, the point looks like x0. y coordinate is 0. And plug it in here. And you will get 0. So that is the first curve. Now the second curve, I want to approach 0, 0, right? If I stay on x-axis, I will get 0 right here. But next, I am going to stay on this curve, y equal x cubed. The points along this curve, they look like x comma x cubed, right? So plug this point in here, see what happens. If I plug there, if I stay on this curve, I will get 1 over 11. So that's what I meant by we choose two curves that are going through that point, by the way. Stay on those and take limit and produce two different results. If that happens, you would say the limit does not exist, okay? So just taking you to calculus 3, giving you an example, because when we are working on the functions of complex variable like this, you want to take limit of this. So you go ahead and take limit of real part and limit of imaginary part. Now that is calculus 3. And sometimes you realize that, oh, well, I can't do it. Maybe the limit of one of them does not exist. If you suspect that limit of one of them does not exist, then you gotta use that example that I gave you. Oh, depending on the function, of course, you will choose different curves, but those curves might be different with different functions. All right. What about the concept of continuity? Now let's look at the concept of continuity. Starting from calculus 1. In calculus 1, you have a function of one variable. Usually, we denote the function by this, y equal f of x, calculus 1. We say this function is continuous at point A if the limit exists and equals the value of function at that point. Very simple, right? If this happens, we say the function is continuous at that point. You know what? We are going to follow the same definition. In complex, well, in calculus 3, we did the same thing. In calculus 3, we said, okay, this function is continuous at point AB if the limit exists and is equal to the value of the function. Now, when it comes to complex analysis, you have a function of complex variable. Because of the same inequalities that I explained earlier, the continuity of this function with the same definition. You take limit exists and is equal to the value of function at that point, the same exact definition. However, if we do this, the continuity of this function will transfer to the continuity of real part and imaginary part. All right? So that, as I said, that set of inequalities that I explained made our life a lot easier, because when you want to take limit, you will take limit of real part and imaginary. If you want to talk about continuity of this function, you examine the continuity of u and v. That's it. All right. Okay. So here is the beautiful fact. This function is continuous at this point if and only if both real part and imaginary part be continuous at that point. Done. Okay. So we took care of limit and continuity for functions of complex variables. Limit continuity goes to their real part and imaginary part. Any comment, any question? All right, I don't see any question. I will continue. And well, it's good to have some facts about continuity. And here are some facts about continuity, I guess. You have seen this before, but if you have two functions that are continuous at a point, so is their sum, their differences, their product, okay? And their f over g, their division. But when it comes to division, we have a condition. We don't want to have zero in denominator, okay? So if you have two continuous functions and do arithmetic, the result is continuous, provided when you are dividing, the denominator be non-zero. What else? Oh, the composition. If you have two continuous functions and the composition makes sense, why not? The composition also will be continuous, all right? Well, the easiest continuous functions will be a constant or just identity function, f of z equals z. And if we use those facts, for example, if you use number 3, where you say the product is continuous, right? So if z is continuous, z times z is continuous, which is z squared, z cubed, and so forth. So that takes us to any polynomial is continuous. Any polynomial function is continuous, okay? If you divide two polynomials, which we call it a rational function, that also will be continuous, provided denominator be non-zero. All right? Denominator, always we have that condition. In mathematics, we don't divide by 0. Okay. All right. Any rational function also will be continuous, provided you exclude zeros of denominator. Okay. All right. Well, so we can of course define epsilon delta for epsilon delta definition of continuity, but we don't need at this stage. what I am going to talk about next will be derivative. Going back to calculus 1 again. In calculus 1, when you have a function of one variable y equal f of x, derivative of this function is defined to be this, right? The rate of values divided by h, and as h approaches 0. Here h is a real number, and x, of course, is real number. We are going to adopt the same definition in complex. So if you have a function of complex variable, this is the variable. Instead of h, now we are going to have delta x plus delta I delta y. I'll tell you what that is. So going through the same definition in complex, derivative at z is f of z plus, this is your h, minus f of z divided by h. Okay? Now, here, the domain is one-dimensional, but in this case, the domain is two-dimensional. So if this is z, you go a little bit to the left or right and up and down. So this is delta z, which is delta x plus I delta y. Okay? So here is z plus delta z is this point. This is z plus delta z. So the value of function at this one minus the value at this one divided by delta z as delta z approaches 0, that is derivative. So we really didn't change the definition of derivative that we had in calculus 1. And for the same reason, I have good news for you. All those rules that we developed in calculus 1 and calculus 2 concerning derivative are valid here as well. So sometimes it's good to know what is definition of derivative and use definition of derivative to find f prime of z. For this function, this is an example, and you are going to have an example, a problem like this later in your test. I will give you a function like this one, and I will ask you to go ahead and find derivative by using definition, all right? By using definition. And by using definition, I mean this, using this fraction, simplifying it, and then taking limit. I just follow this example. Here is f of z. What do I need? In this quotient, I need f of z plus delta z, which means you replace z by z plus delta z. And this is what you get. z plus delta z squared minus 3i times z plus delta z. You simplify this, you square it, multiply out, put the real part together, imaginary part together, all right? Or even if you don't want to do that, remember we are going to, in numerator, we need this, f of z plus delta z minus f of z. If you form the numerator and simplify, this is what you get. Now, this has to be divided by delta z. Okay. You divide it by delta z. Well, here, I can factor delta z out of these three terms. And when you divide by delta z, that's canceled. So you get this. That's not enough. The definition of derivative is you form this fraction, then take limit as delta z approaches 0. Okay, don't forget that part. After forming this fraction and simplifying, now let's take limit as delta z approaches 0 and delta z approaches 0. This part is 0. This is what you get. Done. Okay? It's done. So this is derivative of that function. We expected this because, as I told you earlier, all the rules of differentiation are valid. What do I mean by all the rules? In taking derivative, you had power rule, you had product rule, you had quotient rule, all right? All those are going to be valid. You can use them. You're welcome to use them. Okay. Any question? Any comment? So here are some theoretical fact. If derivative exists, then the function is continuous. Right? Beautiful fact. It's easier to take derivative. Okay, yeah, derivative exists, so the function is continuous. What is it? I mean, what is the reason for this one? Well, the reason is, assume that derivative exists. To show that the function is continuous, you need to show this. Oh, bring this to the other side. So you want to show that f of z minus this, the limit is 0. This is what we want to show. Okay? But I'm going to divide this by this and multiply by the same thing. And now take limit as z approaches z 0. As when you take limit of this guy, which is derivative, exists. And limit of this guy as z approaches z 0, of course, is 0. So you will get 0. It's done. Done. So if the function has derivative, it definitely is continuous. But this is a one-way story, right? This is a one-way story. If derivative exists, you have continuity, but not the other way around. It is if P, then Q. If you have derivative, then you have continuity. But if you have continuity, that does not imply derivative exists. Be careful about that, all right? Be careful. If a function is continuous, it might not have derivative, okay? Now, I'm going to take limit because derivative is limit of this fraction. I am going to examine this limit, if it exists, by two different very interesting way. Oh, here's an example that the function here's the function. Look at this. This is a counterexample. Remember, if derivative exists, the function is continuous. But if the function is continuous, it doesn't mean the derivative exists. Here's a beautiful example. Look at this function. This is a continuous function. The real part is continuous. The imaginary part is continuous. As a result, it's a continuous function. How about its derivative? Well, for taking derivative, we need f of z plus delta z, right? Then we subtract f of z. So this is what we get. Now you need to take limit as delta z approaches 0. You need to take limit of this guy as delta z approaches 0. And I am going to show that this limit does not exist because here is why. I will choose direction, let's say, here's the point, parallel to y-axis. Then you go parallel to y-axis. Delta x will be 0, right? Here is delta z, z plus delta z. If you stay along this line, delta y exists, but delta x is 0. If you let delta x be 0, you get 3i delta y, you get 3. Next, let's stay on a line parallel to x-axis and approach this point. Now on this line, delta y is 0. Delta x is not. So if you let delta y be 0, if you let delta y be 0 here, you get 2 delta x divided by delta x, which is 2. So staying along this line, we get 3. Staying along this line, when taking limit, we got 2 different limits. So the limit doesn't exist, which means the function doesn't have derivative. Okay? The function is continuous, but doesn't have derivative at all. Any comment? Any question? All right. Okay. This technique that I applied here, this technique is a pretty interesting one. And we can apply this technique in general to this fraction. Let's do that. Okay. Let's do that. Remember, when you have a function of complex variable, I don't miss this. All right. Yeah. When you have a function of complex variable, you can write that function as its real part plus I, its imaginary part. I am going to use this fraction and take limit, assuming that derivative exists, okay? Let's assume that derivative exists. So the limit exists. And no matter how you approach that z, or delta z approaches zero, no matter how, you got to produce the same result. All right, let's form this fraction first. So here is, I am going to form the fraction, but staying, for instance, on x-axis and approaching this z. Okay, let's say this is z. I don't need, okay. This is z plus delta z, okay? I better say z plus delta z here, make sure. All right. You have the right. So this is z plus delta z. So here's delta x, here's delta y. Now, if we stay parallel to x-axis, which means delta y is zero, okay? Here, parallel to x-axis, delta y is zero. So here is the fraction, and delta z will be just delta x. I separated the real part and imaginary part. And now, when delta x approaches zero, this part gives me partial derivative of u with respect to x. And this part will give me the partial derivative of v with respect to x, okay? So, since derivative exists, I know that the limit here will be f prime of z. On the right-hand side, though, I will have partial derivative of u with respect to x plus I partial derivative of v with respect to x. All right. Next, I will stay parallel to y-axis, this one. In this case, delta x will be zero and delta z will be delta y, okay? I delta y. So here is the second part. stay parallel to y-axis and form that fraction. Remember, in denominator, we have delta z, which is delta x plus I delta y. But delta x is 0. We simply get I delta y, I delta y. Now, of course, I cancels. And as delta y approaches 0, this part will give me derivative of f, which I know it exists. This part will give me partial derivative of u with respect to y divided by I. This part, partial derivative of v with respect to y. So this is it. So in the first approach, I got derivative equals u sub x plus iv sub x. And here, in second approach, I got this. So since doesn't matter how we let delta z approaches 0, we got to get the same result. Then these two got to be equal, right? These two got to be equal. So the real part is equal to the real part, imaginary part equal to imaginary part. And that gives us two equations. If derivative exists, then u sub x is equal to v sub y, and u sub y will be negative v sub x. These are called Cauchy-Riemann equations. Cauchy-Riemann equations, okay? So they're called Cauchy-Riemann equations. So if derivative exists, we are going to have Cauchy-Riemann equations. This is a conditional statement. If P, then Q. And any conditional statement is equivalent to its contrapositive. Contrapositive means if not Q, then not P. These two are equivalent. So what does it mean? It means if one of the Cauchy-Riemann equations fails, then derivative doesn't exist, okay? Then derivative does not exist. Any comment, any question? Oh, this last part was, I hope you don't get lost in the technicality of proving Cauchy-Riemann equations. But here's the main fact. Here is the main fact. This line. If derivative exists, then we have Cauchy-Riemann equations, these two equations. As a result, if one of these equations fails to exist, or we don't have equality, then derivative does not exist, okay? Let me give you an example right there. This is a, do you remember that function, which is a continuous noise function? All right. Here, u of x, the real part, is 3x. V is 4y. They usually are functions of x and y, but in this case, one of them, well, just that. So derivative with respect, partial derivative with respect to x is 3. Partial derivative with respect to v with respect to y is 4. So we don't have the first Riemann Cauchy-Riemann equation. Remember, in Cauchy-Riemann equation, we require that u sub x be equal to v sub y. And it's not. It's not. They are not equal. So the function doesn't have derivative. All right. The function doesn't have derivative. Okay. Yeah, this is the main thing. This is the main thing. If derivative exists, then this. Now, the inverse, if we have these Cauchy-Riemann equation, does it mean derivative exists? Well, unfortunately not. Not necessarily, all right? We need to impose extra conditions. We need to impose extra conditions for the inverse. If we have Cauchy-Riemann equations, and this real and imaginary parts not only are continuous, but also have continuous partial derivatives. This is the part that I'm imposing. Then derivative exists, okay? Then derivative exists. So, and when derivative exists, we know it's got to be either this or that. They are equal anyway, okay? Here's an example. The question is, does this function have derivative? Well, here is the real part, u. Here is the imaginary part. We called it v. U and v. Let's take partial derivatives. Partial derivative of u with respect to x is 10x. Partial derivative of v with respect to y is 2y. Well, apparently, you see, you're not. But even more interesting, partial derivative of u with respect to y is 1. Partial derivative of v with respect to x is -1. In this one, yeah, we have equality. U sub y is there. But here we don't, okay? Here we don't. But we have equality along this line, though. If we let y always be 5x, we will have equality here. So this function doesn't have derivative except along this line. Along this line, it does have derivative. Or if you stay off that line, derivative does not exist. Any comment, any question? I covered plenty today. Okay. Let's see. Yeah, it's Cauchy-Riemann equation. I will stop at this point because you have plenty of work to do. So let me tell you exactly what I did today based on your work. So last week, I simply covered section 13.1 and 13.2. Well, I was supposed to do 13.3, but I couldn't. But today, I covered 13.3 and 13.4, okay? Today, I covered both of them. So please go ahead and look at those problems. Next time, I will on Thursday, I'm going to talk about 13.5. So, um, any comment, any question? No question. Good. Yeah. Bill Dotson says no question. Marco says no question. Patricia, it says, can you post these notes? No, I don't. I am reluctant to do such a thing. You simply go ahead and read your text. If you are taking the notes, perfectly fine. You read your notes. Otherwise, read the text. And if you can get hold of one of those recommended books, please do so. Read those as well, because I noticed that your book is very brief. And if you can get a hold of one of another complex book, doesn't matter which edition, the one that I recommended, you can find an older edition perfectly fine. They usually have more explanation. They usually have more examples for you, all right? And I am sure you will benefit from having an extra resource. Okay. And by the way, your TA, Abraham, I made your TA responsible for the homework part of your class. I'm sure he explained it to you. So I teach here, and you're supposed to do the homeworks. And on Friday, he will ask you whether he's collecting which part, which section, and he will grade that particular section, right? Okay. Any comment, any question? I don't see any other questions. So have a good day, everybody. I will see you on Thursday. Thank you, Jason. Thank you, Marco, Brandon, Corey, Ernesto, Fox, Bill Dotson. Thank you. Thank you. Trevor, thank you. Have a good day, everybody. Bye-bye now.